Today we're going to take a look at just one quick case, kind of an interesting limit. The limit as x approaches 0, the sine of 1 over x. Now, immediately, what we should think about here is the fact that if we plug in 0, we just end up with the sine of 1 over 0. And we know we can't do 1 divided by 0. 1 divided by 0 is undefined. So this is the sine of something that's undefined, which would be undefined. And this limit actually doesn't exist. But we're going to go through a little bit longer of a process here to prove that this limit doesn't exist. And actually, before we do that, we're going to think about, again, what is a limit, really? A limit is what's happening as we get close to this value of 0, not what happens when you actually get to 0, right? Because this is what happens when we actually get to 0, right? The function's undefined there. And so even though this isn't indeterminate, right? 1 over 0 is not indeterminate. Sine of 1 over 0 is not indeterminate. It's not one of those forms I gave you the other day. We're still going to just first, and this isn't going to work, but we're going to take a look at it because it's kind of interesting. We're going to just do a little u substitution. We're going to let u equal 1 over x. Okay? So if u equals 1 over x, we're going to end up with just a sine of u, right? And we're still going to have this limit here. But instead of having x approaching something, we want u to be approach something. So if x is approaching 0, well, we have to think a little bit about what happens if the denominator of a fraction gets really, 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 really small. Right? If I take 1 and divide it by, let's say 0.000001, that becomes an exceptionally large number. We're actually approaching infinity here. And this is going to be a little bit of an intro to what we're going to talk about when we do limits at infinity. Right? But that's if we're approaching 0 using positive numbers. If we were approaching 0 using negative numbers, we get a really large negative number, right? And so there's just a little bit of a difference there. And this is something we're going to actually take into account next time it's what the idea of what's called two-sided limits. So we're just going to, for now, say that u is either approaching positive or negative infinity if x is approaching 0, right? If x is approaching 0 from the right-hand side, then these values of x are always positive, so we get a really big positive. And if x is approaching 0 from the left-hand side, from negative numbers, then this is a negative number, and so 1 divided by a negative gives you a negative, very large number. So we're just going to, even though this isn't really great notation here, we're going to just say, this is what's happening as u approaches either positive or negative infinity of sine. But we should know what happens to the sine function as the values get really large or really small. Well, nothing different. It just keeps doing the same thing that it always does, right? It just keeps going back and forth between positive 1 and negative 1 and positive 1 and negative 1. It just keeps oscillating back and forth in both directions, both to the right and to the left, right? To positive infinity and to negative infinity. And so again, this should clue us in that this limit doesn't exist, because this one, we're going back and forth between 1 and negative 1, right? We're never actually going to close in on one specific value. Okay, so let's keep all that in mind. And now let's take a quick look at the graph of this function, right? So this is what the sine of 1 over x looks like. And we're particularly interested in what happens as we get close to 0. So as you can see from the graph, it's kind of just a big jumble of mess there. We can't really exactly see what's going on. If we zoom in a little bit, well, the mess doesn't really get any better. We can just see that it looks like this thing is going up to 1 and down to negative 1 a whole lot of times, right? And if I zoom in even more, I can't see positive 1 or negative 1 anymore, but it's still going up and it's going back down. And it just sure seems like the frequency of those oscillations is just getting, smaller and smaller and smaller. Like that, it's going up and back down, much more steeply every time because I can't even see what's going on here in the middle. right? I mean, if I zoom in far enough, it just kind of looks like a big red blob because I've had Desmos graph this in red, right? So it looks like this function is going up to 1 and down to -1, maybe even an infinite number of times as the values of x get closer and closer to 0. So let's see if we can use some of our good old algebra skills to show that that's actually what's happening, that it is actually doing this an infinite number of times. So let's start by seeing when this function equals 1. So when does the sine of 1 over x equal 1? Well, sine equals 1 if the angle is, well, that happens at when the angle is pi over 2. And really that's the only time on one oscillation where this function equals 1, right? If I think about, like, you know, from 0 to 2 pi, right? The only time where sine equals 1 is when x is pi over 2. So what I need is the angle to be pi over 2, and then that'll repeat every 2 pi n, right? Because if I go around a second time, when I get to 5 pi over 2, that'd be another time, right? And at 9 pi over 2, and at 13 pi over 2, and so on. Okay. We'll take a pause on that for a second. Now let's also see, when does this function equal -1? Right? Well, that'd be whenever the angle, which is again 1 over x, is equal to 3 pi over 2. Or another full rotation around there. You can add 2 pi to that, that'd be 7 pi over 2, or 11 pi over 2, and so on. Right? So we'll say plus 2 pi n for this one also. So now we know all of the times where our function equals 1 and where it equals -1. And we're gonna put the constraint in here that where n is an integer, right? Yeah. So we'll say n is any integer. Okay. And really, you know, we could, yeah, any integer is good. So let's now solve each of these for x, right? And this should be really easily done. I mean, all we really need to do is take the reciprocal of both sides. And we could just say x is equal to, and this isn't going to look really nice, but it's just going to be 1 over pi over 2 plus 2 pi n. Now, be careful. I see this mistake a lot in really this entire school year, where people will make a very similar mistake here. Instead of doing what we just did here, which is the correct way, people will say x equals, and then they'll just take the reciprocal of both of the parts. That is not the same thing, right? That is not correct. So don't do that. The other alternative is, if you want to just take the reciprocal of the right-hand side, then you'd have to get a common denominator. You'd have to multiply this by 2 over 2, so it all became one fraction, and then you could just take the reciprocal. But we don't really need to do that. I'm actually not really interested in what this looks like. I'm interested in what those values are when I plug in integers. So we'll do the same over here. We'll say x is equal to 1 over 3 pi over 2 plus 2 pi n. And let's see what happens when I start plugging in integers. Let's say n is 0. So if I plug in n equals 0, I'm going to get x is equal to 1 over pi over 2 plus, well, 2 times pi times 0 is 0. So I just have 1 over pi over 2. 1 over pi over 2 would be 2 over pi. Okay. What about if n is 1? Well, if n is 1, right, then we've got in that denominator pi over 2 plus 2 pi. Pi over 2 plus 2 pi would be 5 pi over 2. And I have 1 over 5 pi over 2, right? We could write that 1 over 5 pi over 2, but really, we're just going to take the reciprocal of that. That's just going to be 2 over 5 pi. So we'll write it that way. 2 over 5 pi. And when n is 2, we're going to get x is equal to, well, pi over 2 plus 2 pi times 2. 2 pi times 2 is 4 pi. So we have pi over 2 plus 4 pi here, which is 9 pi over 2. And that's really just going to become 2 over 9 pi. And hopefully we can see the pattern when n is 3. This is going to be 2 over 13 pi and 2 over 17 pi. And so on. And if we do the same over here with n is 0, we're just going to end up with 1 over 3 pi over 2, which is just 2 over 3 pi. And if we do n equals 1, it's going to be similar to the pattern we had on the other side. We're just going to get x is 2 over 7 pi. You can do the arithmetic on that if you want. And 2 over 11 pi. And so on. The next one will be 2 over 15 pi and 2 over 19 pi and so on and so on and so on. And so we can see that the numerator is staying the same for each of these, but the denominator is getting larger. And if our denominator gets larger in a fraction, that's actually making the number itself smaller, right? These are decreasing. These are getting smaller, and they're getting closer to 0. Same with these ones over here, 2 over 3 pi, 2 over 7 pi, 2 over 11 pi. Those are decreasing. They're getting smaller. They're getting closer to 0. So what this is saying is we're getting to 1 and we're getting to -1 a bunch of times. And in fact, we're going to do it since there are an infinite number of integers. We're going to go up to 1 and down to -1 an infinite number of times as the x values get closer and closer to 0. And so what we've shown now then is that this limit can't possibly exist. Not just because 1 over 0 is undefined when we plug in 0, or because you can't take the sign of infinity if you did a u substitution, but because we've shown that there is no possible way for this function to be approaching one specific number, right? We have answered no to our first question from a few days ago of, is there some number that this is approaching? Well, no, there's not some number that it's getting closer to, right? Because it's going up to 1, back down to -1, going back up to 1, going back down to -1. And it just keeps doing that infinitely because there are an infinite number of integers for me to plug in down here where I'm getting all these x values, right? And each one gets us something smaller and closer to 0, both with 1 and with -1. And so that's our interesting little case for today. We're actually going to stop right there on this one. And next time we're going to talk about a new concept called one-sided limits. We've already been doing two-sided limits, one-sided limits, which aren't really all that much more difficult than the two-sided limits we've been doing. Just some sort of technical things to think about and some specific problem types that you could probably expect to see on the AP test. So that's going to be it for what we're doing today. And next time we'll talk about one-sided limits.